So we have 4 papers in this session, all dealing with various topics of recommendation. The first paper today comes from Carlos Scheidegger from University of Arizona and his colleagues at Utah and Haverford. So.
Thanks, Fernando. Okay. So today I want to tell you about some of the work that I've been doing with Suresh, Sorelle, and some of Suresh's students on feedback loops in predictive policing. So this is something I only recently learned about sort of a few years back. So Predpol is a company whose services are, they do a certain amount of machine learning and they sell the services to police departments. And the service they sell is we can detect where crime goes next, right? So you can use policing efforts more precisely, more effectively, and less expensively. And so what we're interested here specifically is the issue of feedback, sort of what happens when the data that comes from the fact that the system was deployed gets fed back into the system that's going to predict where the policeman should go on the next day, and so on and so forth. So specifically, we're sort of going to look at a small sort of set of the problems that come in predictive policing. And what we want to get a handle on is what happens when your problem is how do you decide where to send policemen next, right? So given historical crime data, you want to decide on some allocation of policemen. And so this is only a small subset of the problem, but I want to make sure that we're scoping this appropriately. We are drawing sort of heavily on some excellent work from Lumen Isak that came out a couple of years ago on significance. And they were, to our best recollection, the first people to sort of engage seriously with this problem of what happens when you sort of take predictive policing systems and you train them with potentially biased data. And they started with this data set that by itself was already really incredible. So they collected the records from Oakland and they built a model of drug usage, sort of. So they actually collected demographic information. They sort of fit a model and sort of given demographic information and density, how likely people are used to drugs. And so they started by comparing what looks like the map of arrests from Oakland, so that's on the top, and the number of arrests, and sort of the estimated drug users on the bottom. And so that already should sort of tell you something perhaps worrying about what's going on there. But even more worryingly, what they found out was the following. So they went ahead and actually implemented the model that Predpol claims their predictive system works. And so this is a combination of like a Poisson term for the probability of crime and what they call these aftershocks that come from like a spatial autocorrelation model that says if a crime happened here, it's probably that's going to happen nearby on the next day. And what they said is, well, what happens if you add a certain amount of crime back into the system from having targeted a particular spot, right? And so they said, well, what happens if we add 20%? And this is where things get really worrying, right? So if you look here, what they're showing is sort of the system runs like once per day, and sort of this is happening sort of throughout time. And so the x-axis here is time. It starts in January, which is when they started having data. And you can see that the sort of distribution of arrests starts diverging fairly significantly from the distribution of what you expect the crime to be. So something strange and potentially very bad is happening there. So this is where we start. And so what we are trying to do in our paper is we're trying to sort of understand a little bit more precisely what happens, right? So what we have is a specific mathematical model, sort of a mechanism that explains why this feedback loop sort of actually occurs. And we're using generalized polyarns. I'm going to explain to you what that is, but for people who've done this, we're using Polyagenberger arns. And what we want to show is evidence that the mechanism that sort of makes these runaway feedback loops, it's actually present in sort of existing predictive policing systems. So we are using Isak and Lum's implementation again, and we're showing sort of this is why it happens. And we developed a way to mitigate this specific kind of problem. And so we're going to identify later in the talk why that goes wrong, and we're going to show one way of fixing this. So before we get to that, I just want to sort of scope down this even more precisely so we're making sure that we're talking about the same thing. So the goal that we're looking for is we are trying to optimize the following problem, right? So we're going to call some policing effective if the proportion of policemen gets sent to a region in sort of proportion to the crime. So you have some allocation of policemen and you want to send it sort of proportionally to how much crime that happens. This is clearly not the only way you can do allocation of policemen to crimes. This just happens to be the one that we're aiming to sort of try to match, and it has the nice consequence that if you end up sort of with this runaway feedback loops, and your distribution of policemen does not match at all the distribution of crime. So we have a lot of assumptions, and so some of these are nice in that they make our problem fairly general, but they also mean that, again, this probably doesn't apply to every single setting in which predictive policing is used, right? So one of the main ones is we have this sort of predictive model that says, well, we are going to send a policeman somewhere, right? So every day we're going to sort of take the data that comes in, and we're going to flip a coin, by which I mean we're going to have some randomness, and based on some random variable that we get to choose carefully, we're going to tell them where to go next. We're not going to store any kind of information about the crime, right? So we're not going to store what kind of crime it was. We're not going to store the sort of whether the suspect had sort of any specific demographic information associated with it. The only thing we're going to store is where the crime happened, right? And that's sort of what we need to do in order to do the predictive policing of sending policemen differentially, but we're not going to store anything else. And we're also going to assume that it is equally plausible that in any region, having a sort of policeman there will result in an arrest with the same proportion, right? Which is, again, clearly not true. So just to make sure that we're all on the same page, right? So let me tell you a little bit about the theory, and so we're going to get a little bit on the math, so just bear with me for this. So the idea that we're going to build a simplified mathematical model that we're going to sort of show exhibits the same kind of runaway feedback that we observe on the actual implementation. And so this is known as a polyurn, and the way this works is very simple. So we are going to model the data that we're collecting about crimes as an urn in which we're going to be collecting balls of different colors, and we're going to model the way in which we decide where to go by sort of reaching in the urn and picking one of the balls at random. And they're going to have different colors. In this case, there's two colors. There's green and red balls. And the way a polyurn works is the following, is sort of we reach inside and we pick a ball, and then if this ball is green, we have some rule that says, if this is green, put this many red balls inside and this many green balls inside, based on the fact that it was green. If it was red, use a different number of colors, right? And so what this does is that we're sort of modeling where to send an officer by the color of the urn that we picked, and we're sort of modeling the crime that happened by how we decide to put extra balls inside this, right? And so as we get more sort of crime in one region, we're going to get more crimes of more balls of a certain color, and so we're going to say, well, there's more crimes in here, so I should go there more often. And so this is a very simple model that is not realistic at all, but what we want to do is we want to study what happens on this model as we sort of feed bad data or good data, or we're not careful about these feedback issues, okay? And so let's start with this very simple example, which is every time a policeman goes to some region, they observe exactly one crime, right? And since they didn't go on the other region, they cannot possibly observe any crime on that, right? So we're going to model this rule by that matrix there that says the first row is the red balls. There's one red ball and one green ball. So if you go to the red region, you never update the number of green balls. If you go to the green region, you never update the number of red balls, okay? And now what we're interested in is what happens as we sort of keep iterating on this. And turns out that sort of very broadly speaking, what happens is that as police record more crime in a region, they're more likely to keep going there because there's going to be more and more balls of that color. And that's fine, that's what we're expecting to happen. But the problem is, as police are more likely to go to a region, they're more likely to get balls of that particular color, which is backwards from what you'd expect, right? So we're sort of letting the feedback, sort of creep into our system. And so the fact that we're sort of predisposing ourselves to collect more crime from one region than the other is kind of the crux of the problem. And so it turns out that what we can do now is we can study what's the distribution of red and green balls in the urn as we let this process go, right? I sort of let the predictive policing learn what it may, and let's see what it looks like. And the first result, and this is not ours, this is a classic result from polyurns, says that with the rules that I have here, the system doesn't learn anything, okay? So more concretely, the system learns something that's got nothing to do with the fact that there's about a 50-50 chance of crime happening, right? So you sort of record a crime in the red region, you record a crime on the green region. It should be the case that this should converge to about 50-50. That's not what happens. So here's an illustration that I'm going to be using sort of throughout the rest of the talk, so I just want to give you sort of how to read this. Okay, so time goes from left to right. And so in the beginning of the system, sort of, we don't know what the probability of the crimes are, and so things fluctuate wildly. And sort of what I'm recording with color here is the density of the estimation. And so there's about 10 different runs in here, and so you can sort of follow the system as it sort of running. And so all of these are running with the same probability of replacement, okay? And so you see that for some of the runs, the system starts believing that there's about a 90% chance of happening crime in the red region. For other runs, it thinks that there's an 80% time of other region. For some of them, it thinks that it's 50-50, but there's sort of nothing at all happening here, right? And so if we run this for 1,000 runs, you can see that it's equally likely that we'll get anything on one side or another. So it's not learning anything. So something's going bad. We can do the same thing for sort of more complicated models. So the second result that sort of, again, is classic and known is that if these two numbers are different, the EARN just sort of completely oversaturates with one of the two colors and nothing else of the other, right? Even though it's a 2-to-1 ratio, what happens is that this sort of just becomes entirely one of the crimes. So it doesn't learn anything. There's something bad here, right? The actual model that we use is something a little bit more complicated, which is the fact that even though we're sending a policeman to the red region or to the green region, sometimes there's crime that happens on the other region, right? So we sort of have to take into account the fact that someone might report a crime from the other region, and so you might add some balls to your EARN even though you didn't go there. And so the formula for what happens in the limit is a little bit more complicated. We're not going to get into the details of that. Sort of there's, this is a result that already is on the literature. But the point is, it still doesn't converge to the relative crime rate. So even with reported crimes sort of being reported at a correct rate, this thing diverges. So what do we do about it? And this is where our sort of actual technical contribution comes here. And so the intuition is as follows. We want to mitigate this problem somehow. We want to break this feedback chain. And what we observed is the following, is that if the police is often much more likely to go to region A than to region B, in a sense you shouldn't be surprised if you see more crime in region A than in region B, right? Because you're going there, right? Of course you're going to see more crime. And so concretely speaking, what we do is that we downweigh the regions in which we go more often, right? So we had a rule that says that if you're 10 times more likely to go to region A than to region B, because you believe that the crime rate is 10-to-1, then what you should do is you should only take into account about 1/10 of the crime that you see there, right? So you should be much more surprised to see a crime in a region that you believe there's not enough crime than the other way around. And what we prove in the paper is that if you use this rule, then things actually convert to the true sort of region and the true relative rate of crime. So this is a very nice, very simple rule. And the nice thing about this is that even though it's sort of very contrived model based on EARNs, we can actually sort of take this rule and apply it to other settings. And if you've done unequal weighting sort of survey sampling, right, you know this rule about sort of hard-to-reach populations, which is a Horvitz-Thompson estimator, right? It says that if you have a population that is 10 times as hard to reach, you should weigh them about 10 times more. This is very much the same thing, right? So we have the proof on the paper. I don't want to sort of bore you with more math, but the point is, without improving things, the sort of distribution of the relative rate diverges. But with our technique, it sort of learns the right distribution of the crime rate. And so that's encouraging, right? So I wonder if we can actually sort of now make this make sense with actual predictive policing algorithms, right? So this strategy is nice, but it's sort of very limited. So does it work on the things that we care about, specifically on predpol? So again, what we do is we take Lumen Isak's implementation of predpol, and we add this rule that says, if you believe on your current estimate that you're 10 times more likely to go to region A than to region B, we are going to forget about 90% of the crimes that happen in region A. We're just not going to put them in, because you're already predisposed to see that, right? And then we can run the simulation over and over again and see whether it actually matches the relative crime rate. And well, it does. It's hard, we don't have any sort of specific like mathematical proof about this, but using our sort of policy now, things tend to converge on the line that we should expect. This is the relative crime rate as the model expects it to be. And now this is where it actually sees. And so we believe that this has the right kind of mitigation effects. So that's nice. However, I want to make sure that sort of, we're scoping this down appropriately, right? So we notice this problem of feedback. We can show you mathematically on this very contrived model that it happens. But this is not evidence that PredPol is sort of fundamentally broken, right? It sort of shows one way in which the model can go wrong. And we are also not saying that with this fix, everything is good. We're showing one way in which this one specific problem can be fixed. So the other issue is, again, without getting into too much detail, the Harvard-Thompson estimator has very high variance with low probability events. And so we're not saying anything about the resulting efficiency of this. It might take a long time to learn about the crime rate. So what we think should happen is you should actually use the right kind of thing from the beginning. Instead of trying to use these models that don't know about feedback, you should actually just use things from reinforcement learning. And if you're interested, we can talk more offline. There's sort of semi-bandits algorithms that we're presenting at OUT 2018, which kind of do something a little bit better. So I just want to acknowledge again that this would not have been possible without their implementation. And thank you.
So my question is, so you're modeling policemen as agents and crime as an event, or discovering crime as an event, but criminals are agents. And the better resourced the criminals, the more likely they are to not go where the policemen are.
Right.
Can you counteract that? Because this is a question I don't know the answer to. Can you counteract it by weighting certain kinds of crime?
So we did not deal with strategic behavior on this paper. There's this whole subfield of game theory called Stackelberg games, which look at sort of allocation and strategic behavior like this. And I don't know specific results about runaway feedback on those cases. It would be fascinating to study. But we very explicitly didn't think about those. But the term to Google for is Stackelberg games. So.
Okay.
Hi, Deborah Stone, Brandeis University. Thanks for a great paper. I'm curious about what you're taking as the standard of the actual crime rate, because as we know, the crime rate is what police say it is. It's who they decide to arrest, and then who the rest of the justice system decides actually committed a crime.
So this is an excellent question. We are using what I think is a very good model. It's clearly necessarily a simplification, but again, it's Lumen Isak's model based on demographic information from Oakland, plus sort of surveys on drug use, and so we're using that as the base rate. But in some sense, what we are doing in terms of like the arrests is we're just using our compensation term, right? So we have to use some assumptions. That's a model we are using, but thank you.